recording. Very first thing on the recording is, if you're not doing participation, if you're not doing the Google form, that's where participation points come from. Sorry, if you're here, you already know this. So there we go. No other administrative questions, comments, things to announce, things to deal with? Great, let's do it. Yes, you could put anything on your equation sheet. Yes, you need a Scantron. There. Those are some other things that should be in the front of the recording. For today, I have had a bunch of people said, can I go please? And I'm fine with that. Let me give you the equations. Let me give you a front-loaded lecture. And then if you want to go, if you are mentally dead, if you cannot learn anymore, if your brain is so happy that you're happy with what you've learned so far, then get out of here. Not yet. Don't get your hopes up. In a second. In about 20 minutes. The remainder of the class is anyone who wants to practice for the final. I will give a review for circuit problems, and if we got some time, intro to magnetism problems. But yeah, we're at the point of the semester where my FTG level is matching up with all y'all's. So let's go. Here's the front-loaded thing. Waves. We introduced them last time. Yes, question first. The lab. Yes, ha, 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 ha. The last lab before the final is, I need to triple check with my colleagues to make sure they're happy with this, is going to be moved online. Merry Christmas. So you do not need to physically come in for the last lab, at least for my last labs, and I'm going to triple check with Drs. Bailey and Huston to make sure that they're okay with this. It'll be online. It'll be a Zoom. I think. We'll see. Yes. So the study guides that I always like to do are more practice problems. I will post last year's final. I will, yeah, I will post last year's final, and we'll have lots of examples of things. And I'm running additional problems in here. It is up to you to say, all right, here's a problem that I don't know how to do. What do I need to know to do it? I'm not going to make an itemized list of this problem is this topic, this problem is this topic. Study guide is lots of problems for me. I dimly recall that I think once upon a time, I might have read something that says that actually boosts scores to do it that way. Or maybe I'm just reasoning based on what I want to be true. I think I dimly recall. I do definitely recall making equation sheets for students. Forcing you guys to make your own equation sheets actually bumps a couple of percentage points up. Not based on me, based on educational research. That forcing you guys to do it makes you think more. Anyway, other questions? Did I answer your question, Brandon? Yes, good. Let's get to it. Okay, so the short micro version of this lecture is, what's a wave? A wiggle in space and time that propagates out at some wave speed. Wavelength is the distance that that pattern makes along the medium. The distance from, say, a peak to the next peak. And there is a foundationally important equation, V equals F times lambda, that relates wave speed, wavelength, and frequency. Y'all have seen that equation in the lab, all but like 3 of you in both sections, yeah? We're going to talk about that a little bit. Also, like all but 3 of you have seen in the labs, there is an equation for wave speed. Wave speed is a property of the medium, not a property of the wave. Wave speed, let me say that again. Wave speed is a property of the medium, not a property of the wave. Just like resistance is not a property of the electricity, resistance is a property of the resistor. Wave speed is a property of the medium. Just like frequency is a property of the spring oscillator. Frequency is a property of the oscillator, not the oscillations. Okay, so the formula is square root tension over density. You saw that in the lab manual, most of you. Density in this case, I want to warn you, is kilos per meter of length of the string. It is not your usual chemistry grams per cc, not grams per volume. It is kilograms per length of the string. The last equation that I'm going to present to you is the idea of intensity. We're going to do a couple problems with intensity. Intensity is how we perceive brightness or loudness most directly. Intensity is power divided by area. Very few people in the 3 o'clock class do this. Do you guys know the surface area of a sphere? It is not 4/3 pi r cubed. It is not 2 pi r. The surface of a sphere is 4 pi r squared. 4/3 pi r cubed is the volume of the sphere. But if you want to know how much paint it takes to paint the outside, the surface area, that's 4 pi r squared. Just the r. Otherwise, I would say 4 pi r squared. Some people voted 0 exclamation mark. I registered that as 1. 0! 1. Anyway, silliness aside. No. Okay, those are all the equations. If you're totally dead, get going. If you would like to see the introduction to these things, stick around. I'm going to keep this relatively compact. It's not actually that much material, so I don't think that this is going to take more than half an hour to actually explain it in my standard pacing. At that point, I'll say you can get going if you're dead then too, yeah? Here we go, traveling waves. I introduced this before. Would I mind writing out the equations? They are on the next slides, except for Kristen, will you remind me, I did forget to write the 4 pi r squared. Will you remind me too, when we get to area, to remind people 4 pi r squared? Thanks, okay, good. What's a wave? A wave is a pattern of energy that spreads through a medium. That's it, bang. A wave is a wiggle that spreads around. We will talk about many kinds of waves in the couple of remaining classes we've got. Waves do not travel at constant speed, but for now we're going to talk about when they do. If light always traveled at a constant speed, if light always traveled at the speed of light, my glasses would not work and I would die. So, fortunately for me, light can be bent as it passes from one medium into another, and you can have curved, light slowy downy regions, also called glasses lenses, that bend light and do useful tricks with changing speed. But we're not talking about that yet. So we're just going to talk about waves in one medium where the wave speed does not change. Wave speed v is the speed of the wave, big shocker there. I'm going to skip ahead because I already did this last class. If you want, review last class. Distance equals rate times time. The distance that a wave travels in one period is lambda, wavelength. So I can say distance equals rate times time turns into wavelength distance equals rate v times time, period. I think I wrote this in the lab manual. You will often see this written as that. V equals f lambda. Wave speed equals frequency times wavelength. And I can't write this down without banging this drum a couple of times, playing the same theme that I've been playing before, but in my experience it's necessary. F doesn't control V. Lambda doesn't control V. What controls V? Medium. The medium. The medium controls the wave speed. Just like you did in lab, frequency times wavelength always multiplied up to the same number. If you wanted to change that number, you had to change something about the string, the tension on the string, the thickness of the string. Thickness. No, those all those strings are maximally thick. Oh yeah, physics lab room string. Silliness aside, V equals F lambda. F controls lambda. Lambda controls F. Their constant of inverse proportionality is the wave speed, but wave speed is controlled by the medium. We did an example of this last time. We're on fast forward mode. I will do an example of this further if you wish, but if you can multiply F times lambda to get V or divide V by F to get lambda, I'm going to go ahead and skip ahead. Wave speed. What controls wave speed? It's not the wave, it's the medium. And we're going to talk about a couple of different, no, we're going to talk about one. We're talking about one medium, the stretched string, and that's it. That's the only thing that I'm going to give you an equation to find. But let me play that theme. What does resistance depend on? The resistor. What does capacitance depend on? The capacitor. What does the frequency of an oscillator depend on? The oscillator itself. Not the oscillation, not the current, not the voltage, not the charge. An oscillator's frequency depends on properties of the system. The electronic components, resistance, capacitance, inductance, although we didn't talk about that, depends on the properties of the component. The frequency of a wave is free. You can have any frequency of wave, but the wave speed, V, is the property of the system. I do want to make this point. Frequency of an oscillator is a property of the oscillator. The frequency of a wave is free. It could be anything. For sound, frequency is pitch. Big frequency.
Little frequency.
For light, frequency is color. Lots of different frequencies. Here, let me. Oh, these projectors suck so bad too. I don't know. Here. Very high frequency. Also very high, but lower frequency. The frequency numbers for visible light are in the, I think, 10 to the 14 hertz. One with 14 zeros after it hertz. Very fast wiggles. Okay, so frequency could be anything. You could have a wave of lots of different frequencies. What causes the frequency of that wave? Ultimately, it is the frequency of whatever is starting the oscillation that makes that wave. So, for instance, if you have blue light, ultimately somewhere there's an electron that is being shaken around really fast. If you have red light, that electron is being shaken around slower. All light ultimately starts as charges accelerating somewhere, being shaken around back and forth. The difference between an atom, the difference between an atom that releases a red photon, releases a blue photon, is those atomic energy level transitions between adjacent quantum states are higher energy or lower energy, being shaken faster or slower. Those are properties of the system, incidentally. Question? The question was, blue is 400 nanometers, red is 700 nanometers. Yes, the lower the frequency, the bigger the wavelength. Nanometers is a measure of wavelength. The higher the frequency, the smaller the wavelength.
So when something's getting like closer to you, like extremely fast, like stuff getting like redshifted and blue shifted, how is the frequency getting changed when it's getting closer to you?
That is actually Doppler effect, which is the topic of next lecture. Ask me next time. There's neat physics in there, but I want to keep each day a bite-sized chunk. Or stick around after and ask. Okay. Is good? Is good? Is good? I like these questions. Let's keep going. Wave speed for a stretched string is bang. Tension divided by linear mass density. This is kilos per meter of length of the string. Square root is wave speed, right there. Tension is newtons, it's a force. Mu is kilograms per meter. You take the mass of the string, you divide it by the length of the string. I'm glad you asked. For the people who have not yet done lab, which is 90% of y'all, there is a common mistake that I've seen for year after year. In the lab manual, in the lab procedure, we talk a lot about the length from the fixed pulley to the point where the oscillator is vibrating the string up and down. We talk about that as the length of the string, the length of the vibrating portion of the string. Yeah, déjà vu, remember? Let me sketch it. Ring stand. Come on. No red. Got the ring stand, you got the string vibrating with some sine wave, you got a pulley, you got some weight down here, yeah? Okay, very often in the lab manual, I refer to this as L. This is an important length. This is a good way to find wavelengths is by looking at how many wiggles there are in a certain length of the string. Do not use this length when measuring mass density. If you take the string or cord over to a scale, are you just measuring the weight of this? Or are you measuring the whole darn thing? If you want the density, don't take the total mass divided by some smaller fraction of the length. Take the total mass divided by the total length. Yeah? If you want the density of a person, not yet, Christian, 2 seconds. If you want the density of a person, would you take their total volume and divide that by the mass of their head? No, you take their total volume and their total mass, right? Also, I hope you don't know the mass of just the head very, very easily. I think it's far easier to do it when it's all together. So to get the lab mu value most accurately, take your string, stretch it all the way out, measure his length with a ruler or a meter stick. Take the total string, set it on the scale, measure his mass directly. That's your mu, kilograms per total length, not just kilograms per wiggling length. Yeah? Great. That said, what's the big theme? The frequency of the wave speed of the waves does not depend on the waves themselves. They depend on the medium. Sound waves in air. There's a formula for it that I can never remember. Depends ultimately on density of the air, humidity, temperature, maybe some other stuff that I don't know. As I said, I don't remember it. For us, when we deal with problems with sound, which I will give you the number. Speed of sound is 343 meters per second, whatever. When we talk about light, we will say the speed of light in a vacuum is a constant, 3 times 10 to the 8th meters per second, so on and so forth. Anyway, this, I don't think a single person got this wrong in the 3 o'clock section. If you can multiply and take a square root in your calculator or a square in your calculator, you're golden. Shall I skip and come back to it at the end for people who wish for additional practice? Great. Here, this I do want you to think about for a second, though. I am so addicted to teaching you guys to reason about proportions. Question, what are we, D? Tell me the answer to this one. Oh, you want to see the question too? That costs extra. I will remind you how does T have to change for V to get twice as big? $300. Oh, that was a different question. The answer is not 300. Okay, it wants another second. Correct answer is 4 times. I didn't see any wrong answers. I saw some blank answers. Maybe people who checked out. There we go. 4 times. If I make T 4 times what it was, the square root of 4 is 2. I have double the final formula. Likewise, I'm going to move past that. And this I have cut out from the class. This was not a review exercise because that was a previous part. Do you feel about this? Like we've introduced a lot of this before. Do you feel comfortable with this? Do you feel happy with this? You're all cozy and warm and cuddly inside with this material. Yeah, that's what I was thinking. Here's energy and intensity. It's one equation, and I got to remind you of a geometry fact. And that's it. Applying it well, I'll give you some practice problems here, and we'll see how well you do. Waves carry energy. Duh, right? You go out into the sun. Wow, it's hot out there. Where did that energy come from? It's not magic, it's the sunlight. It might be evil magic. Maybe it's evil waves. I don't know. I define intensity as power per area. Power per area. Power carried by the waves. Energy per second, remember. Power in watts. Watts power. Area is the cross-section that radiant energy is passing through. That is to say, for instance, if I am exposed to this projector, what I see, brightness looking into that projector, what I would use to find the power delivered to me is, I guess, the area of my pupil, right? Pupil, yeah, pupil. Hey, by the way, do you guys know, I don't know, not all of you have taken anatomy. Do you guys know the part of the eye that actually sees the light? Like, where does the light get received by? Yeah, the retina, but very importantly, is it the entire white of the eye? No. Everyone knows that the light that goes into actually where it is seen has to go through the hole in the middle, the black part. Yeah, the black part. The white part, or bloodshot if you're me, part of the eye does not actually notice any light. It has to go through the hole in the middle. Okay. Hey, by the way, how do you hear? What hears? Does this hear? Does this skin hear? No. What part of the body actually receives and interprets the sound? Where does that sound actually have to strike? Yeah, okay, that's too deep. Yes, you know more than is necessary. The eardrum has to strike the eardrum for that energy to propagate down into the cochlea and be received by the tympani. Whatever. Okay, that's beyond me. Okay, so what shape, by the way, is the pupil? Circle. What shape is the eardrum? Circular, roughly, approximately. Great. What about energy as it spreads out? Think of the sun. Won't you think of the sun? I think about my son all the time. Both of them. All three of them. The one up there and the two that live on Earth. The sun, energy is spreading out in all directions, every direction you could possibly go, not just the rays that hit the Earth, of course, right? And just going out every direction. Why is the sun much brighter on my summer home on Venus than it is out here in Phoenix? You know, I go to Venus for summers because it's cooler there. Why is the sun dimmer when you take a spacecraft out past Jupiter? The power, the energy of the light flying through space. Space itself does not absorb energy. So why does it get dimmer the further away you are from the star? Distance! The distance increases. Area increases, intensity goes down. This is why starlight from Alpha Centauri isn't as hot as the sun. Alpha Centauri is a rather brighter star than Sol, than our sun, but we're rather farther away. The area that Alpha Centauri's energy is spread out over is astronomically large, so that energy has such a low intensity. Alpha Centauri puts out more watts per second, puts out more joules per second, has a greater wattage than our star, but that energy is spread out over a region of space that is impossibly large. David?
The area is not the area of the pupil, it's the area that the light travels.
So I brought up the pupil and the eardrum for a reason. If you wish to know just how intense the experience of staring into a light source is. What energy, where do you care about the energy? Do I care about the energy that is bouncing off the screen here? No, I care about the energy that is passing through my pupil. But if we're talking about the total energy emitted by something, where does that energy go? I need to consider, where are those waves passing? Where are those rays going? From a star, from a candle flame. If I hold up a speaker, if I wave it back and forth like I just don't care, that sound energy is going out in every which direction. If you are asked a problem, if you are trying to calculate how loud, how bright something is, you need to care about both factors. How is the energy passing around? And what aperture am I using to receive it? Let's do an example. No, let me give you a picture first. Very important. If light is passing through an aperture that you know the size of, use the area of the aperture and you can calculate the relationship between the intensity and the power directly. But what about if light is spreading out, if sound is spreading out, like a star, like a speaker way up in the air, like a candle flame? Light goes out, rays go, energy goes out in all sorts of directions. And when you're closer in, you've got more of that energy piercing. It's densely packed. It's the same total amount of energy. It's just packed denser because you've got less of a region for it to be passing through. A laser pointer is very collimated. Its area doesn't change much. I think there's a theorem that says you can't have something perfectly collimated. If you take a laser pointer and shine it at, Alpha Centauri Alpha, Alpha Centauri 1, whatever, Alpha Centauri, the first planet around Alpha Centauri, that laser pointer, when it reaches 4.7 light years away, is going to be spread out the size of the planet. But, over macroscopic distance from here to that wall, the dot of the laser pointer doesn't increase appreciably in size, so I'd still use that area. How loud does a train sound at the end of the tunnel versus right next to the train? About the same. Because the energy of the train whistle, horn, whistle? The energy of the train alarm sound does not change the area it is spread out as it passes through the tube of the tunnel. This is important, by the way. Hey, is everyone thinking through this? Not just David? As a sound wave from a train that is going through a train tunnel passes through the train tunnel, the area does not change. And rock is a pretty darn good reflective thing. It's not absorbing the energy. So if you listen to a train whistle, that sounds wrong. If you listen to the sound of the train at the entrance to the tunnel, and then you walk to go get hit by the train inside the tunnel, it sounds equally loud just before you die. Fun fact. I actually haven't tested that fact, but I believe the physics bears it out. Have you tested that out, Brandon? Huh? I'm assuming that the tunnel does not change its cross-sectional area, that the tunnel is roughly as big as the train. We don't have a huge cavern and then it shrinks through the exit tunnel. I don't know. Disneyland would probably be very different. Those going through a ride where you got a room and then an aperture, then a room, then an aperture, probably doesn't apply. I'm thinking of a train passing through a tunnel cut through a mountain for it. This is exactly where I want the 4 pi r squared. Okay, so the whole moral of the story, the whole immoral story here has been, think of where the energy is going, and I want to present a formula here. The surface area of a sphere is given by the equation 4 pi r squared. The surface area of a hemisphere, you guys know what a hemisphere is? Equals 2 pi r squared. Half a sphere, half the surface area. And the area of a circle is pi r squared. I think this is everything you need to know for your homework. You don't need to know the exact cross-section of some shapes. If you know that they don't change, for instance, then you know that the area doesn't change, the intensity doesn't change, the power doesn't change, everything is the same. Question? Ah, but the sun is sending energy out into outer space, regardless of whether we are turned towards it or not. Day or night has no effect on the energy the sun is putting out. If you were looking at the energy absorbed by a solar panel here on Phoenix, it's at some patch of the Earth, then it matters whether it's day or night. I'm imagining the sun shining out into space, energy being sent every which way out from the sun. Yes, yes, yes. For that matter, you might be asked a question about a solar panel. A solar panel of given dimensions picks up sunlight. I would then care about the length times height of the solar panel area if I'm trying to get from the intensity of sunlight to the power that solar panel has available. In every case, thou shalt think about where is the energy going or being, what is it striking or where is it passing out, and use the intelligently chosen area formula. Here are some formulas you may need. I am not saying that you should only pick from these three choices. Yeah? Okay. Let's do a problem. Here's a problem. Test yourself. If you get this and the next one right, then that's an indication that maybe you can go. Think carefully. There are 2 steps to this problem, and work with each other, by the way. Oh, and let me see where you guys are at. What is this? Google Form E? Read carefully, by the way, read carefully. Excuse me. Good, Jacob. If you feel done, you may get. Zainab, good job. Hannah, good job, you did it. Kaylee, good job, you did it. Gerardo, good job, you done did it. Sabrina, good job. Brandon, womp womp. Google works. Type the calculation in Google. Dan, you got it. Pamela, good job. You don't have to go because I'm calling your name, by the way, but I'm telling you got this medium hardness right on the first try. If you feel mentally dead inside, you may leave. Holy crap, this is a lot of people getting it right. Yes. Ryan, yes, good. You DK, you did know. Okay, here we go. Here's how I tackle this sucker. Here's how I rugby tackle this problem. Intensity at 1.0 meters equals 0.1 watts per square meter. 30 times as far, the area has increased by a factor of 30 squared. So intensity at 30 meters is it 10 to the minus 4? Is it? Blast it. I have to run it again. 0.1 divided by 900. Yes, 1.1 10 to the minus 4. That's not the final answer, eh? Then I say, this energy, this 1.1 times 10 to the minus 4 watts per square meter is striking what? It's striking an eardrum. The eardrum of given geometry here, what can I calculate from that? Power that is available for the ear to turn, the sound energy available to turn into nerve impulse. And if I recall correctly, this is 6 point something times 10 to the minus 9 watts. 6.2, I think. Is it? And to be very nitpicky, how much energy is transferred in 1 second? That many joules. If the power is 6 nanowatts, in 1 second you get 6 nanojoules. I was very smug, pleased, happy, rejoiced to see a lot of people got this right. Question me though. Does this make sense? Can you visualize it? Can you taste it? Don't taste ears, but can you taste it in your mind's eye? Don't taste eyes either. Hell, if you're a cannibal, don't let me tell you what or what not to taste. Take it back. As long as you're not tasting me, taste whatever you want. Do another one, do another one, do another one. You get this right, then I think you really got it. How bright is it on Mars? There's the question. Please note if your final answer comes up brighter than on Earth, then you did it wrong. Mars is further out. There's very little atmosphere on Mars. Actually, atmosphere has nothing to do with solar constant either. It's the sun's intensity at our orbital radius, not the sun's intensity on our surface necessarily. You'll never get that 1.36 kilowatts in a meter squared panel because atmosphere. But that doesn't mean that it's not 1.36. Anyway, try the problem, try the problem. Mia, you got it. Kylie, you got it. She's got it. She's got it. That's a song, right? Dylan, he's got it. That's what I sing to myself about all y'all, except for the people who don't go by she. Marissa, good job. Haneen, good job. I want units though. Sabrina, good job. Pamela, good job. Too many sig figs, but good job. You got it. Sammy, Mariana, Dylan. I already said Mia. You're all good. Jeffrey, I think I already said you. Zainab, I think I already said you. Still good. Remy, good job. Okay, okay. Bunches of right answers. Not everyone. Most. Good. Let's work it out. Just like a constipated mathematician does, let's work it out with a pencil. Oh, not even groans. Oh, okay. Thank you. Okay, very good, very good. You get an A. What's the physics here? The power of being sent through outer space, the power is the same. We have increased the distance, the area through which the energy is being passed. So what I could say is that oh, for dog's sake, the intensity, let's set this up as a ratio problem. The intensity at Mars compared to Earth, we're going to get, what fraction is Martian sunlight compared to Earth? Some unknown power divided by 4 pi r Mars squared, 4 pi r Earth squared. And power, 4, and pi are all the same. So what does that simplify to? 1 over r Mars divided by 1 over r Earth squared turns into r Earth over r Mars, both squared. Let me pause for a second to make sure you fractioned right. Did you fraction right? Does anyone want to ask about why? No, you believe me? You trust me? It is worth it if you're done doing a exam problem or whatever to think for a hot second. Mars should be weaker sunlight than Earth. If you write this fraction down and you get, well, hold on, Mars is bigger distance than Earth's orbital distance, so this fraction is smaller than 1. Yep, that checks out. At this point, before you do any further numbers, if you get a bigger number over a smaller number, that would say that Martian sunlight is brighter. No, that can't be right. Okay, what is 1 AU? I don't know. Well, I do, but you don't know. But you do need, what you can immediately say is that if 1 AU is the Earth sun distance and 1.5 AU is the Mars sun distance, then this ratio is 1 to 1.5. Okay, then at the end of the day, we say the sunlight is 44% as bright. If this is how much power I can extract in an ideal solar panel on a cloudless day on Earth, that's how much power a NASA robot or whatever robot can extract on Mars for a 1 square meter solar panel on a cloudless day, perpendicular to the sun, if it's plugged in. Turn to your neighbor. Talk about the entirety of today's lecture and then ask me a question in the Google form. Google form G is tell me what's hard, if anything. Where is the light leaving the sun? Does the light go in laser rays? Or does light go in every direction? No, but I do know that light is going in every possible direction from the sun. You don't have to just stand on one place to see the sunlight beaming at you. But it's not spreading out hemispherically from the sun. Light goes in every direction from a star. You don't see a sun or a star just in one direction. Try it. Look at the sun. Not directly. Move your head a little bit. Do you still see the sun? The backside of the sun is still radiating light. It doesn't matter that that energy doesn't point towards you. Energy leaves in every possible direction from the sun. That light still goes further and further in those same directions, spreading out in a spherical shell of increasing and increasing and increasing size. That energy spreads out with decreasing intensity according to the square of the distance from the star, from the sun. Yes, but first I reasoned about how bright it is out there. If the energy itself doesn't change, just the area that it's passing through, I can use this to reason that it's 44% as bright out there. And then I could say, all right, that's the energy density at the Martian orbit. What fraction of Earth's, no, that's the energy density at Earth's orbit. If it's 44% as bright at Earth's orbit, then we get this much intensity. Mars gets that much intensity. But I'm not asking for the energy itself. I'm asking for the energy density, watts per square meter. You don't need the square meters. You would need the square meters to get the total energy felt by Mars itself. Intensity doesn't tell you energy. Intensity tells you how densely packed that sunlight is. Yes. Well, be precise. The power of the energy of sunlight is constant. When it's right next to the sun, those light rays are really densely packed. The same energy in those light rays as they spread out, getting further and further from the sun, illuminating a greater region of space, it gets less dense. There's still the same amount of energy in those light rays, unless they happen to smack into a planet or whatever. Planets occlude an impossibly tiny fraction of the entire sunlight. Yeah? Yeah? Okay, I gotta give you 1 minute to get out of here, and otherwise I'm putting a practice problem for the final on. Too late, time's up. Here we go. Resistance is not futile. Resistance is 5 ohms. 97. So you also don't remember Star Trek, The Next Generation. 97, okay. David, what year were you born? What year were you born? Do you remember Star Trek TNG? 2000? You were born in 90, okay. Well, that was TNG, Next Generation. Do you watch TOS or TNG? Kirk was TOS, Picard was TNG. Yeah, okay. Okay. So you did watch the original series, the 60s Star Trek.
Yeah. Cool. Very progressive for their time. Very. I was surprised.
An interracial kiss. My son is shocked at interracial kisses when it's between his parents. Because Cerny's Sri Lankan. And anyway. Okay, so the question is, if this is a voltmeter, what does it say? If this is an ammeter, what does it say? Here, I'll write these down. Oh, I am confused. Good. Let's have a question. I'm confused in the rock concert example. Okay. People who are working on the exercises. Is Anjali still either present in the room or online? Great, okay. So let me ask, if you wish to start the example review problem is, what does that say if that's a voltmeter? What does that say if that's an ammeter? Two different questions. Anjali asked a great question about the rock concert example. They said, you solve for energy, but energy is constant. So are we solving in power? Is there a difference? Total energy leaving the speakers is one thing. Total energy, what fraction of that energy leaving the speakers is received by eardrum? That's what I ultimately asked for. I don't tell you how much energy the speakers put out. I don't tell you the energy at the speakers. I tell you how dense the energy, power, is packed 1 meter away from it. You could use that to calculate the energy coming out of the speaker if you know the speaker size, but you don't need to care about that. All you need to know is that once that sound wave has left the speaker, that energy is going to dilute itself by a factor of 1 over r squared. When the distance from the speaker doubles, the area that wave is now passing through is 4 times as big. If the distance triples, the area is 9 times as much area. Every time you increase, by whatever factor you increase your distance from, the area of the shell of region of space that energy is passing through, that non-changing energy is passing through, that area increases by a factor of r squared. You could find the total energy and use that to then calculate the density later, but the fast way to do this is just to say the sound wave itself does not lose energy. Energy is a constant, power is a constant. It just gets weaker because the area increases, and area increases quadratically. So if I'm 30 meters instead of 1 meter, I am 1 over 30 squared as intense. That's the first step. Does that click? You want me to write it down? Okay. Second step is to say, all right, now I know the intensity at your face. If I've got 1.1 10 to the minus 4 watts per square meter, that means if my eardrum were a square meter, ugh, gross. If my eardrum were a square meter, I would be getting that many watts. But my eardrum isn't a square meter. My eardrum is this big. So if you've got this much area, you would get that much power out. You need to multiply by how big an area you've got to get what fraction of the energy in the sound is available actually to be received. That's why at the end of the day, I said the total energy per time, the total power, is the area times the intensity. All I'm doing is I'm shuffling around the equation. Power divided by area is intensity, and then thinking what changes, what's the same, what changes. So when you've got a given intensity, you know how loud the intensity of the sound is in a place, you could find out how much your eardrum is absorbing of that by multiplying power, intensity times area is power. Well, what I asked was, what is the energy in 1 second? Energy per time is power. That's why I was going back and forth saying energy, power, energy, power, energy, power. Because I said energy per second. That's the definition of power. If you know how long you want to know, power and energy are interchangeable. You can convert one to the other. Power is energy divided by time. Multiply. Yeah. Power times time is energy. That's it. Yeah. Good. I think there was another. I'm confusing myself as to which. Okay, so another person. Let me ask: is Brian still with us online? For God's sake, that sounded ominous. Are you Brian? You're not Brian. Okay, so I'm not going to answer that. How bright is hilarious. Kaylin? Is Kaylin here? Kaylin asked a good question. Hey! Kim? You're Kim. Okay. Kim asked, oh, okay. I'll answer Kaylin and Kim's question. Why did I flip R Earth over R Mars squared, I Mars over I Earth squared? Because area is downstairs. You had a fraction of energy per area. You take that fraction over the other fraction over Earth, over Mars, flips when you make it into one fraction. Simplify the fraction, that's all. Sure. And Kaylin online asked one final, why did I not convert 1.36 kilowatts per meter squared to watts per meter squared? I did. It is totally interchangeable, watts or kilowatts for me, with which way you answer. Yes.
What do you put up with Earth over Mars? That there was a ratio difference.
Oh, wait, no, I do want to know Mars per Earth. What is Mars compared to Earth? Did I write? No, I did. Martian sunlight intensity relative to Earth. Since I've got a radius in the downstairs, fraction over a fraction, Earth switches upstairs. The downstairs of a downstairs ends up upstairs. Here, Mars over Earth, Mars over Earth. Radius of the Earth, radius of Mars. I'm just plugging in this numbers that I gave into this equation. This is the orbital radius of Earth. This is the orbital radius of Mars because this equation. Yeah, you see it now? Great. Okay. Shall we do do? This one? Okay. This is a little harder. Let's do voltmeter first. To know this one, do you want more time to do it? Because people were thinking about the this week's stuff. Do you want more time to wrestle with this one? Squeak an hour, forever hold your pee. No? Okay. Suppose we got a voltmeter. Problem one, find out what happens if this is a voltmeter. What does a voltmeter draw? What's the resistance of a voltmeter? Infinity! So you might as well erase it. Whoopsie, not all of it. Might as well erase it. Open circuit. Yeah? It will. It will. But if I'm analyzing the circuit, I need to know where does electricity flow and how much. And the very first thing to analyzing the circuit is to say, all right, if the voltmeter is essentially an open circuit, I can just analyze the three resistors first. What happens if you've got those three resistors connected to a 9-volt battery? Said the blind man? Okay, so tell me about the electricity flowing through this. What do you know? What can you deduce? That's where we always start. What is the total resistance? Add them up, exactly. 5, 10, 15, 30. Okay, so I've got 9 volts and 30 ohms. What do you know then? Immediately. 0.3 amps, verb, baby. Okay, so there's 0.3 amps leaving the battery. Where does that 0.3 amps go? What do we know about current in series? Doesn't change. If 0.3 amps leaves the battery, it has to flow through that 5 ohm resistor. Every single microamp of that 0.3 amps has to leave the 5 ohm resistor. Every single picoamp flows into the 10 ohm resistor. Every single femtoamp flows into the 15 ohm resistor and then back to the negative terminal of the battery. Current everywhere is 0.3 amps. So is my answer 0.3? No, I asked for the voltage. If you know that 0.3 amps is flowing through this circuit, what is the voltage that that voltmeter would register? How could you find that? There is a very, very easy mistake to make here. Why don't you put it in the Google form? What do you think if 0.3 amps flows through that 5 ohm resistor, for instance, what is the voltage registered by the voltmeter that I've hidden? So 0.3 amps is flowing through the circuit. 0.3 amps flows through 5 ohm resistor. What is the voltage registered here? Show me in the Google form. Show me what you think. What are we at? Question H? I've got to vote for nothing. I've got to vote for 1.5. I've got to vote for 9. I've got to vote for 7.5. I've got to vote for 42. Just kidding. That is the answer, though. It's not the answer to this problem. Another vote for 42. Oh, I was being silly, Gloria. Okay. The correct answer is 7.5. Here's how. What's the total voltage available for the electricity in the circuit? 9, right? How much voltage is absorbed in the first resistor? That is the meaning of V and V equals IR. If I start with 9 volts, then absorb 1.5, how much is left for the rest of the circuit? 9 minus 1.5 is 7.5. Do you see? I can elaborate in excruciating detail if you wish. This branch and this branch is effectively in parallel. They experience the same voltage. We could also do the exact same analysis by saying how much voltage do these two drop? And you know that voltages in parallel are identical. Voltage across 10 ohms, 3. Voltage across 15 ohms, 4.5. Total voltage of those two in series, 7.5. Another way of saying that there's 7.5 felt by the voltmeter. Third way is to recognize this is a cheater trick. Voltage across a resistor in series, across a bunch of resistors in series, the voltage across each resistor is proportional to its fraction of the total resistance. If I've got R1 and R2 ohms in series, R1's total of the total resistance, R1 divided by R1 plus R2, R1 divided by its total, is the same thing as his ratio of voltage compared to the total. So 10 plus 15, 25 is 5/6 of the total resistance. That's 5/6 of the total voltage. Bang, you're done. Again, the principle, this is called the voltage divider circuit. Principle is each resistance's fraction of the total voltage is the same as his fraction of the total resistance. Pick away, whatever you like. Cheater way. First way, just whatever you do, don't say V equals IR gives me the voltage at a point. V equals IR gives you the change in voltage across that R. Next problem. I replace this with an ammeter. What happens? It shorts. Very good. It shorts, be precise, it shorts what? The 10 and the 15 might as well not be there. Why? Because ammeters have effectively no resistance. An ammeter presents, by design, presents as little opposition to flow as possible. If you're measuring a flow, you don't want to get in the way of the own flow you're measuring. So an ammeter intentionally will guzzle up all the current and nothing will flow through the 10 and the 15. There is no such thing as a perfect diameter. Very little will flow through the 10 and the 15. Great, how much total resistance have we got? Total voltage? How much total current flows? 1.8 amps is the correct answer. So, things you got to know for this. Resistor addition, principles of spheres in parallel. Ammeters have low internal resistance, voltmeters have high internal resistance. And the meaning of V equals IR. Not the voltage at a point, but the change in voltage across that component. Why don't you turn to your neighbor for 2 seconds, or talk to yourself in a high-pitched and low-pitched voice, and then ask me a question. People online, what you thinking? If there are any still listening. Last chance for questions before I close the recording. Okay. That wasn't it.